Okay, in this video lecture today we're going to look at a couple different things. The first thing we're going to look at is crystallization and growth of materials. And again, this is kind of following up on the design lab projects that you're working on for the next several weeks. And then also we'll follow that up with a little brief discussion of some of the analytical tools that you use to characterize nanomaterials. And that's primarily the scanning electron microscope and a technique known as X-ray photoelectron spectroscopy, which we can use to determine the chemical composition of your particles. So to begin with, we started talking on last Wednesday about crystallization and growth, and one of the important things here is to just recognize that when we think about growth of a material, there's really two steps. One is what's called nucleation, and nucleation is basically forming a particle out of nothing or forming a bubble out of nothing, and then growth is pretty much everything that happens after that initial bubble or crystallite has formed. And these are relatively complicated processes that involve absorption, diffusion, and many other processes, but in general we can understand a whole lot about what happens with some fairly straightforward thermodynamics. So the basic idea is that if we think about having an interface between two materials, and first I'm showing it in a spherical model, so this would be appropriate for either forming bubbles in a liquid or forming, say, raindrops in the atmosphere, or forming a spherical particle in a liquid or a gas. There's basically a couple terms. When we think about the total free energy associated with these processes, so you know, for example, from the solubility product, how to calculate the free energy change associated with forming a solid from ions in solution, and normally you assume that that free energy change is basically total. The total free energy is proportional to the amount of material that you have. And so that means that the free energy change per unit volume is the same, and if you have 3 times as much material, then the volume will be 3 times as much, and the free energy change will also be 3 times as much. So basically just this idea that the free energy change is proportional to the volume of material that you have. Now it turns out there is a second term that is typically neglected, but turns out to be very important when you get to small objects, and especially when things get down to the nanometer length scale. And that's based on the fundamental idea that anytime you have an interface between two materials, whether it's a solid liquid, solid gas, liquid, that there's an increase in energy associated with the atoms that are right at the boundary between these two materials. And you can think of it very simply as a result of being under-coordinated compared with the materials that are in the bulk. But fundamentally, the important thing here is that this term is always positive. It always costs you energy to form an interface between two materials, whereas you know, for example, that under some conditions it can be energetically favorable to precipitate a solid. So these two terms are sometimes in opposite sign. And if we look at a solid, so here is basically representing that now instead of spherical particles as a solid, you can again see what happens that if we think about having a little tiny particle, essentially all of these atoms are at the surface. If that particle grows a little bit, we now have some at the surface and some at the bulk, but still most of them are at the surface of the particle. And then as it continues to grow, now most of the atoms are in the bulk and a relatively small number are at the surface. So most of the time when we think about bulk materials, we're sort of thinking about things in this limit where, because the vast majority of atoms are present in the bulk, we sort of neglect this little surface term that is this term right here. On the other hand, when we get to the nanometer scale, you can see that an increasing fraction of the atoms are present at the surface. And the important thing here is that these guys are in under-coordinated sites. So whereas an atom in the bulk would be surrounded by 4 nearest neighbors, or if I were to draw this in 3 dimensions, it would probably be surrounded by 6 nearest neighbors. These guys at the edges are maybe attached to only 3 atoms, or the guys in the corner might only be attached to 2 atoms. So these guys have inherently higher energy by virtue of the fact that they can't adopt a normal sort of molecular coordination because all of its neighbors are all on one side. And so the net consequence of that is this idea of a positive surface energy, or what is often called surface tension. And this term has units of either energy per unit area or force per unit length. So the consequence of that is if we think about how these two terms scale, the volumetric term, if, for example, the formation of a solid is energetically favorable. So in your case, for example, it might mean that the solubility product or that the product of the concentrations of two ions exceeds the solubility product, and therefore thermodynamically it should be energetically favorable to form the solid. That means that it's energetically downhill. And if we look at the energy as a function of size, that simply follows as 4/3 pi r cubed. So the more stuff we form, the more the total energy changes. On the other hand, this 4 pi r squared term is positive, and so that means that in the end there's a balance of forces that is always such that as we begin to form an interface between two materials, so again this could be the solid in a liquid or the bubble in a liquid, that you always pay a price at the very beginning to nucleate that little bubble or to form that first little bit of crystalline solid. And once you get beyond a certain size, it turns around and it becomes energetically favorable to grow again. But this idea that there's a barrier to forming a bubble or to nucleating a solid in a liquid is called the activation barrier to nucleation. So the nucleation process, again, refers to this initial formation of a tiny little particle, and you can see that that is energetically unfavorable. And then once you exceed a particular size, it's called the critical nucleus size, then it turns around and it becomes energetically favorable to grow the particle. So again, it's hard to grow small particles. Once they exceed a certain size, they'll tend to grow bigger. Now, just as a demonstration of that, here's a little video that shows carbon dioxide in water. So this is Sierra Mist soda, and this is supersaturated with carbon dioxide, so it's thermodynamically favorable for it to form bubbles of CO2 in the liquid. And you can see that, you know that a pressurized or a carbonated beverage doesn't release all of its CO2 immediately. In this case, we see that there's a lot of bubbles that are forming, or a few bubbles, that are forming way down at the bottom of the glass. And the reason for that is there is some scratches in the bottom of the glass or other sites where the CO2 can exceed the critical nucleation size. So again, the reason that your soda doesn't completely fizz the minute that you open the top is associated with this critical nucleus. Now here we just added some sand, and the sand is just silicon dioxide. It simply provides some nucleation sites, and you saw that the instant that sand was added to the liquid, there was a dramatic increase in the rate of CO2 bubble evolution. And that is the same thing, the idea that once you exceed the critical nucleus size, it's very easy for the bubbles to grow. So in this case, we dropped little particles of sand into the soda. That made it very easy then to make bubbles around that little particle, and you saw that the CO2 gets evolved very quickly. So from a thermodynamic standpoint, this is pretty well understood. And what it says in the case of a liquid, for example, is that if you look at what happens as you try to form a particle, for example, like a nanoparticle in a liquid solution, and you imagine, for example, looking at what happens as a function of time as you increase the concentration of the things that should form the nanoparticle. So again, that would be the concentration of copper, for example. If you were to slowly increase that initially nothing would happen, and there would be this barrier that would be achieved, and then once you get over this barrier, then you get both nucleation of particles and you get growth of the particles until then eventually that concentration profile begins to decrease. So in this particular case, you're manually increasing the concentration. Once you begin to form nuclei, now growth becomes favored, and the concentration in solution will decrease as you go along. So this idea of the critical nucleus size also means that when you try to grow small materials like nanoparticles, there's a number of phenomena that happen. One of the other things that we often refer to as what's called Ostwald ripening or coarsening. And essentially what that means is if we have particles that are around this critical nucleus size, it often becomes energetically favorable for the little ones to go away at the expense of the large ones. So the little ones will essentially tend to evaporate. They'll tend to, if we have a particle that's of this size, for example, there's a driving force for it to go down in size and basically release those ions that it's made of back into solution, and the larger ones will grow. So if we were to look at the size distribution of nanoparticles as a function of time, we might see that, well, we might have some distribution of sizes at some point in time. Here's the critical nucleus size. If we were to look a little bit later in time, we'd see that these guys will all tend to evaporate because they're over here. These guys would like to grow. And so this size distribution basically bifurcates until eventually all the little nuclei are gone and you're left with much larger particles. So controlling the size distribution turns out to be fairly tricky. We don't want the particles to grow very large. And so in the case of your experiments, for example, it means that if you were to grow your nanoparticles and leave them sitting at some high temperature for a relatively long time, they will like to continue to grow. The smaller ones will like to go away at the expense of the larger ones, and what you'll end up with is a small number of very large particles instead of a large number of very small particles. So this process of Ostwald ripening or coarsening is one way of controlling the size distribution of the nanoparticles. Now, there are ways that you can also control the shape of the nanoparticles. So as I illustrated it earlier, we had a relatively simple structure or a sphere. Now, of course, with solids, they're composed of, for example, say positive and negative ions. So in your case, it's copper and oxygens, copper oxide. And with a solid, you have the possibility of exposing a number of different crystal faces. Some crystal faces will have equal numbers of cations and anions. And one consequence of that is that these particular crystal faces, as I've represented here, would be electrically neutral overall. It would have equal numbers of positive and negative charges, for example. On the other hand, you can imagine that suppose that I make a solid under conditions where I might have preferential adsorption of one kind of ion. A good example of this would be if you were forming a silver chloride precipitate by taking a high concentration of chloride in solution and adding a little bit of silver. Then you would always have a large excess of silver present in the solution, and you would tend to build up an excess of silver ions on the outside of the nanoparticle. With different more complex crystal structures, like you have in copper oxide, you can often have inherent differences between, say, this face and its opposite face. So one face might be terminated with gold atoms, another one might be terminated with green atoms. And so that gives rise to a number of interesting phenomena. One of the interesting phenomena is that oftentimes when you're growing these materials, as in your design labs, you also have a variety of different organic ligands that are also present in solution. And these ligands can bind to the surfaces of the nanoparticles, and they change the overall energetics quite a bit. They can act as a diffusion barrier so that ions that are present in solution simply physically can't make their way down to deposit on the surface. And so this idea that these ligands can bind preferentially to certain crystal faces. So if we imagine, for example, the gold atoms are positively charged, and in solution you might have some carboxylic acid containing species. Those will tend to preferentially bind to the cations on the surface, and they will block then the further adsorption of cations onto the surface, or I should say anions, onto the surface, whereas other crystal faces might be accessible to growth. So this is a common way of changing what's called the habit of a crystal. The habit refers basically to the shape of the crystal with respect to the various crystallographic axes that are, or crystallographic faces that might be present in a solid. A very famous example of that is the growth of gold nanorods or nanowires. So in your lab, you're looking at how some of these different ligands and different chemistries between Benedict solution and Fehling solution, for example, might change the shape of the nanoparticles. There's actually two fundamentally distinct ways that you can change the shape of the nanoparticle. One is by the preferential adsorption of these ligands onto a particular crystallographic face. And so a very famous example of that is the adsorption of what's called CTAB, cetyl trimethyl ammonium bromide. This is a quaternary amine. So quaternary amines are positively charged, and it has a corresponding anion, which in this case is bromine. But this positive charge preferentially binds to certain crystal faces of gold. And so if you start with gold nanoparticles, like we have down here in the bottom, and you expose them to CTAB. The CTAB binds preferentially to one crystallographic face. This represents the CTAB head group, that tetramethyl ammonium, and it forms actually a bilayer where we have the tetramethyl ammonium bonded to the gold nanorod and also sticking out in solution, and this region in between basically acts as a barrier so that reactants that are in solution can't find their way to the edge of the nanoparticle. They can only find their way to the edge. So if you put in CTAB, a little bit of gold plus, and a reducing agent, what you find is that you spontaneously grow rods instead of particles. And here are just some examples of nanorods that were grown by a collaborator of mine, Kathy Murphy at the University of Illinois, who's somebody who spent a lot of time trying to control the shapes of these rods. And you can see you can get pretty precise control over the diameter and the length of the nanorods by controlling the composition of the solution. Here's an example of just thousands and thousands of little gold nanorods. This is a transmission electron microscope image, so there are some variations in darkness that have to do with the crystallography. That's sort of an artifact of the way the imaging is done, and you can see a few small round nanoparticles that are left, but by and large, very homogeneous growth of these asymmetric nanoparticles. Now, this growth of nanorods is something that's really of tremendous interest right now for lots of reasons. One of them is that large asymmetric nanostructures can essentially serve as wires. They can act as electron highways, and that's a strategy that many people are employing to try to make next generation photovoltaic devices like solar energy converters, where you want to have a lot of surface area for the material, and you also want electrical conduction along one direction, and so some of these can be as wires. So I mentioned there were two fundamentally distinct ways that one could make growth preferential in one direction. And the first one was this idea that because different crystal faces inherently have different energies, that one can use those inherent differences in energies and then amplify them by using the organic ligands like CTAB to act as barriers to reaction along particular crystallographic faces. You can make things like gold nanowires or nanorods. A second way is to make use of the inherent crystallography of what's called a screw dislocation. And so a screw dislocation you can get by just imagine taking a perfect homogeneous solid and shearing it so that you push one side up and one side down. And that creates a defect like this. It's called a screw dislocation. Okay? And imagine now what happens if we take more atoms that are in solution. Each of these little squares represents an atom, and these come down and begin to deposit on a surface. So the first one comes down, and this has very high energy if it's sitting out on the open plane because it has a coordination of only 1. When it finds the step edge here, it has a coordination number of 2 or 3. And so as we deposit these individual atoms from the gas phase or from the solution, they'll wander around, but they're pretty unhappy if they have a relatively low coordination number, and so they will diffuse until they can find a step edge like what one has at the edge of the screw dislocation. Now you can also see that what happens is once those atoms have come along and have bonded to the step edge, essentially this little step edge of the screw dislocation has simply moved forward. And if we were to continue this process, we would find that this little shear plane, or the screw dislocation edge, would basically spiral around and around and around. And as we added more and more atoms, it would basically form a spiral. So these so-called growth spirals are very well known for a range of materials. The picture on the left is a static image of graphite, and you can see what would be called the dislocation core would be right in the center here. So when you shear, as we showed on the previous slide, there's almost like a line defect that extends down through the length of the material, and where that line defect comes out at the surface, there is that little step that I showed, and you can see then the growth occurs in sort of a spiral way. Over on the right here I have a movie. This is a movie that was made of solution phase growth using something called an atomic force microscope. These things right here are steps. So you can see the surface is a little higher here than here, higher here than here. So as you go around this, there is a series of steps. So it's basically like a little bit of a spiral staircase. And the dislocation core is in the middle. And what you'll be able to see is that this is now going to be placed under supersaturation conditions. And so you'll begin to see what happens as the material actually begins to grow. So what you can see is at the core, it seems to be turning clockwise, and what you're actually looking at is that little step edge as it is, go back to here, the step edge associated with shear dislocation is wrapping around counterclockwise, and we're getting more and more material deposited. The important thing is the screw dislocation is a defect that can never heal, and essentially as you deposit more and more material, it simply grows and grows and grows and becomes this giant spiral like you can see on the piece of graphite here. Now, if you have a wire, imagine that instead of having a large planar surface, imagine that you started with, say, a nanoparticle, and that nanoparticle had a shear dislocation in it, or a screw dislocation, that again, that screw dislocation forms a little bit of a step edge. Atoms that come raining down from solution onto this edge will rattle around until they find that step edge, because that's the site where they can maximize their coordination. And as that occurs, this step edge would basically wrap around clockwise, right? Atoms would add on right here. The step edge would move. It would rotate clockwise. And as that process continued, we would continue to add more and more material. And as that happens, we can continue to grow many, many layers, and it simply makes the grout longer and longer and longer, and you end up with this screw dislocation that turns into a nanowire. So in the case of copper oxide, there is a lot of evidence from the work done by Professor Jin's group that many of these one-dimensional wires or many of these original nanoparticles will have screw dislocations. And so by changing the solution composition, you can sometimes get preferential growth along one dimension. Whether that occurs also depends on the relative growth rate of atoms coming in from the side and depositing along the shank of the nanorod versus along the end. You can see that as the nanoparticle gets longer, that there's more surface area along the periphery of the nanoparticle than there is at the edge, and so that also will control the aspect ratio that you might expect for nanoparticles that are growing in solution. And of course, you have a number of different chemical constituents, including things like glucose, in your reactant mixture, and so if those molecules preferentially absorb along the side of the tip, then you will potentially be able to change the aspect ratio of the nanoparticle. So in the end, it's this complex interplay of growth rate, temperature, time, composition, and one of the things that we are, and many other people are interested in understanding, is how do you use this to control the growth of nanoparticles in such a way that you can make these long one-dimensional highways that are of great interest for things like solar energy conversion. And of course, as I mentioned earlier, copper oxide is particularly interesting because for solar conversion, you'd like to have materials whose band gap, and again, the band gap is the difference in energy between the valence band and conduction band, and the valence and conduction band are equivalent to the HOMO, the highest occupied molecular orbital, and the LUMO, the lowest unoccupied molecular orbital, respectively. And so that controls the range of wavelengths of light that can be absorbed, and copper oxide is a nearly ideal match to the solar spectrum. And so in principle, if one can use materials like copper oxide to collect sunlight, you have the possibility of really maximizing the overall efficiency of the process. Okay, in the next part here, we're going to take a look at a couple of the methods for characterizing nanomaterials. The first one's going to be the scanning electron microscope. So, okay, the first question is why electrons? So the reason you want to use an electron microscope instead of an optical microscope is that there's a fundamental limit in optical microscopy known as the diffraction limit, and using visible light, you can't resolve anything smaller than about 100 nanometers in size due to diffraction. The the relationship between energy and wavelength is established through what's called the de Broglie relationship. And the important thing here is that the de Broglie relationship, as shown on the right, shows that the effective wavelength of a particle can be represented as about 12.2 angstroms divided by the square root of energy, where that energy is measured in units of electron volts. So if we have electrons of about 5,000 eV energy, square root of 5,000 is about 25, so we have a de Broglie wavelength of something like half an angstrom. So the important thing there is we can easily measure with very high spatial resolution. Okay, so the basic idea in the electron microscope is we come in with a primary electron, and again this will have energies from 30,000 to 5,000 electron volts. When that electron crashes into our sample, which is represented by this blue stuff here, some of those electrons will be ejected directly backwards, and those are called backscattered electrons. And they are the same electron that came into the sample and basically just ricocheted straight back. Usually that occurs by the electron hitting the nucleus. The larger number of particles will be scattered forward and will create other ionization events, so that one high energy electron in creates a number of secondary electrons. And these electrons can then in turn induce other ionization events, and we get sort of a plume of electrons within the solid, and some fraction of those electrons will come back and be emitted, where they can be detected using a detector. And this detector is essentially just like a photomultiplier tube. An electron hits it, kicks out secondary electrons within the photomultiplier tube or electron multiplier, and we get a cascade of electrons toward the end that we then detect as a current. So the actual microscope itself has a number of different parts. So first off, we've got an emitter tip that has a bias applied to it with respect to our sample of some large voltage, with the negative being on the tip. That tip will emit electrons that will pass through these electron lenses and be focused down onto the sample. Near the bottom, there's a set of deflection plates or coils. And the job of this deflection plate is to steer the electron beam around across the sample. And so they can steer the electron beam left and right, as well as in and out of the page. And in that way, they can basically raster scan over a rectangular area that basically constitutes eventually the image. And you can see that the electron beam does penetrate into the material as well. And again, when it does that, it creates these backscattered electrons represented in blue that will basically go right back up into the electron microscope, and also these lower energy secondary electrons that were shown in red on the previous slide. They get amplified. We get to measure a current. That current is measured by a computer and presented on a computer screen. And the image basically represents a map of the total number of secondary electrons collected as a function of the XY position of the electron beam. So we represent that intensity in a grayscale. So if there's a lot of electrons being kicked off, we represent it as white. If it's few electrons, we represent it as dark. And that intensity of electron current is represented as a function of the XY position of the electron beam on the sample. And if you do that, here's an example of some of the images that you get. The upper left one, this is iron oxide, basically rust, and you can see there's a scale bar. These little nanoparticles are anywhere from roughly 20 to maybe 30 nanometers in diameter. Here are some titanium dioxide nanotubes. These are hollow wall tubes where the diameter is again something like 50 nanometers. Here are zinc oxide nanorods, and here's a blown up image of the zinc oxide nanorods. And if you look at this one in particular in the lower right, you can see a very clear, nice hexagonal shape, and that's just a result of the crystal structure of titanium dioxide, or zinc oxide, has 6-fold symmetry. So you can learn a lot about the crystallography by looking at these. Now, one question is, what is it that generates the contrast in these images? And there's basically two things that give rise to contrast. One of them is what I'll call topographic contrast. And that's because as we steer the electron beam around across the sample, there will be shadowing effects. So for example, if the electron beam is pointed at this location on the sample, we have a direct path for those electrons to make it over to the electron multiplier. and they will yield a current. If that same beam is steered to another location that might be on the left edge of this little structure here, more of the electrons will go off to the left and fewer of them will go off to the right, and we'll see a smaller amplified current. So as we raster scan the current back and forth, we'll see more or less current, and essentially the image in that case looks very much like if you were to place your eye at the position of the detector. You'll see some things being bright and some things will be in shadow, and you will see them either with lower intensity or not at all. There's a second kind of contrast that comes in play if you have materials with different atomic numbers. So here, this represents something like a gold particle embedded in some other matrix. And as the electrons come down, if they're hitting the blue material, there will be some yield of electrons that go off to the detector. And if it's hitting gold, then we will get some different yield of electrons going off to the detector, maybe more, maybe less, depending on the material. And then for heavy elements in particular, they tend to have much higher efficiency of scattering electrons directly back from where they came. And so there's a special kind of detector called a backscattered electron detector that results in something that is often called Z contrast. So Z being the atomic number. And so the amount of current coming back here basically tells you something about the chemical composition, because heavy elements will scatter electrons more effectively back into the backscattered electron detector. So qualitative, at least, then the important thing is to know is that there's two different mechanisms by which you can generate contrast in the SEM, both topographic and elemental or chemical contrast. Okay. So here's an example, again, of some of the things that you can do. You can actually use the electron microscope to make things. Essentially, you can use the electron beam to pattern structures on surfaces, and that's a technique known as electron beam lithography that turns out to be a very powerful way for making structures and devices on very small length scales. This is one that my group did a number of years ago, which is nanobucky. So this is the world's smallest badger. He's about 15 microns across, and he's composed entirely of these little 50 nanometer little carbon nanofiber hairs. And again, here are some other examples of things that you can do, and you can see more or less the shadowing contrast between the different materials. The second method for characterizing nanomaterials is X-ray photoelectron spectroscopy, and this is really intended to give information on the chemistry of the sample. So the basic idea here is if you think about what is the electronic structure of a solid material, you're used to thinking about the electronic structure of atoms and maybe small molecules. So we know, for example, that atoms will have 2 electrons in a 1s orbital and 2 electrons in a 2s orbital and some variable number in the 2p and subsequent ones. If we take a material like that and instead of having just a single atom, we condense it into a solid, there's a lot of interactions between these that result in formation of hybrid orbitals. And the important thing there is that the orbitals that are involved in chemical bonding are usually called the valence orbitals. So we have a valence band. The empty ones up here lead to something called a conduction band. And these bands are very broad, very large number of energy levels, very close together, very little structure that you can use for chemical information. But the core levels are actually pretty sharp. They do not hybridize very much, and so the 1s orbital of an element in a condensed solid will be essentially as sharp it is in the original atoms from which it's made. So if we imagine having a solid whose electronic structure now looks something like this, so we've got, again, 2 electrons in the 1s, a filled 2s and 2p, and maybe some intermediate filled valence bands. If we come in now with a high-energy X-ray, and that X-ray has a sufficient energy, as given by the E equals h nu relationship, then it will be able to kick out electrons from both the valence levels and these core levels. If we kick out an electron from the core level, it will end up with some particular kinetic energy. And that kinetic energy is controlled by energy conservation. We come in with an X-ray of some well-defined kinetic energy that's controlled by the X-ray source. We can measure the kinetic energy of the electrons after they're ejected out of the solid, and then by energy difference, the energy of the X-ray minus the kinetic energy of the electron gives us the binding energy. Okay, so we can rewrite that in a couple of different ways, but it's basically energy conservation between these three quantities. And so the binding energies are very characteristic of the elements, and we can then do very direct elemental analysis of the sample. So the way the instrument works is graphically shown here. We'll show you a little video in a couple minutes, but essentially we have an X-ray generator and an X-ray monochromator. That X-ray monochromator is made from a diffraction grating, and that diffraction grating is essentially a crystal. So the atoms within a material like quartz can serve as a diffraction grating. It's a curved diffraction grating, so that instead of having two mirrors and a flat diffraction grating, we simply have one curved diffraction grating, and that basically puts the monochromatic X-rays into the center of a vacuum chamber. The sample's in the middle of that vacuum chamber. It kicks out electrons, and we measure the kinetic energy of those electrons using something called a hemispherical electron energy analyzer. It's similar to the kind of ion analyzer that would be used in mass spectroscopy, except that here we're measuring electrons, not ions. So electrons of different kinetic energy will traverse different paths through this analyzer, and then we have an array detector at the end that is able to measure the intensity of emission at various energies. And this functions sort of like the CCD array in an optical spectrograph. So in the end, we end up measuring intensity as a function of energy. And if we do that, we get a map that is, on this scale, it's the number of counts per unit time, so the emission intensity of electrons. And here's plotted the binding energy. And you see peaks at very well-defined energies, and these can be very easily identified. You can basically march up the periodic table from carbon to nitrogen, which isn't present, to oxygen to fluorine, and you can see that the peaks basically march up in direct order. And there are many, basically every element in the periodic table can be analyzed using XPS except for hydrogen and helium. Here's lithium down here. And so the cool thing is we get a complete atomic map, or an atomic composition of the sample in one shot. And then the second thing it can give us is there are smaller changes in the binding energies due to local changes in oxidation states. So now we're looking just over a very narrow range of energies centered around that carbon peak. So that carbon peak is about 285 eV. If we blow up and look very closely at that peak, we see it's actually comprised of a number of peaks depending on the composition of the sample. So this actually is a diamond sample, so it's pure carbon, and it gives rise to just one beautiful carbon peak. This is carbon in the form of fibrinogen. Fibrinogen is a protein. It has a number of different carbon in the form of alkyl chains, alcohol groups, and carbonyl groups. And you can see that the carbonyl groups, for example, have higher binding energy. So essentially what happens if we bind carbon to an element that is more electronegative, like oxygen, that oxygen pulls electron density away from the carbon, and what's left, then the electrons that are remaining on the carbon are now more tightly bound, and they have a higher kinetic energy than that of the alkyl chains. And here would be an alcohol like carbon would be somewhere in between. So the important thing there is that we can get information not only about the elements that are present, but also about their oxidation states. And so in the case of your projects, where we're looking at copper and would like to know, do we have copper 1 oxide or copper 2 oxide, or has the copper 1 oxide disproportionated into elemental copper and copper 2 oxide, we'll be able to tell that by looking at the distribution of the copper binding energy. And also one can determine the stoichiometry. XPS is a quantitative technique, so by analyzing the areas under these peaks, we can determine the absolute elemental composition. And so in the case of the copper oxide, we should be able to determine the stoichiometry of the sample by quantitatively analyzing the oxygen and the copper peak. There is no copper in the sample that's shown here, so you don't see that. Okay, so that's it. What we're going to do now is take a couple quick videos, look at what the instruments look like, and you get a glimpse of the inside